Alright, welcome back. It's the same day. It's about 5-10 minutes after I just shot that previous video. It could be days later with regards to YouTube, but for me it's right now. So we're going to utilize the reflection formula that I literally just proved to solve an incredibly awesome series that is very closely related to the Basel problem, which was, of course, the sum over the reciprocals of the squares of the positive integers. Solved by Euler in the 1700s. I mean, it would have to be the 1700s because that's when he was alive. That blind boy, all of his math, all of his mathy books. If it was my trademark, I'd have an Euleroid fly by right now, but what could I do instead? We'll have to see. Okay, so let's just get to the series. Me! Papa literally just did this. I mean, like a month ago. Like, well, maybe 2 months ago. God damn it, you son of a you. I can't believe it! I didn't know this was a thing, and then he went and did it. God damn it. Okay. Fine. Fair. Fine. Like, if he had done it 2 years ago, then I would do it. But I mean, it was 2 months ago, and I mean, he's doing the exact method that I was going to use. Because, I mean, what other method is there? That's funny. Okay, fine. What's next? Okay, I have a couple more representations of gamma. Let's just go over that. Let's just do that. Yeah, we'll do a couple representations of gamma instead. So, this one also involves the Riemann zeta function. And I just realized something that I didn't know about. There's an interesting study of series that are called rational zeta series, which is like, or rational zeta sums, which is like where you have the Riemann zeta function plus a thing, maybe 0, but the Riemann zeta function plus a thing, times some sequence of rational numbers, and then add it all together gives interesting results. And there's a lot of cool things that prove that. For example, we proved that the sum over all of the Riemann zeta function values minus 1, so just the fractional part of all the Riemann zeta values in the original definition add up to 1. All of those things divided by the integers that you're plugging, like zeta of n minus 1 all over n adds up to 1 minus gamma. We showed that in our very recent video. And so I might want to explore rational zeta functions more. I can't believe he just did it. And I didn't even watch the video. You son of a I was so excited! Alright, so let's just do these cool representations of zeta. Papa. Okay, so from my video about the series and things that equal 1 minus gamma, you may recall me using this fact. And I didn't use x and k, but it's the same fact. And in this case, I'm going to need, and in this video I'm going to need that one. The plus version. So this minus can go in there, but then we're going to get a factor of -1 from all of these. So we get a -1 up here, and then another k, and then another factor of k -1s there. So we have actually -1 to the k plus 1. I believe that's correct. And so we're going to utilize this fact today. We're going to do another zeta-y thing, but I need to first jump back to one of the first videos I did on the Euler-Mascheroni Constant and talk about the idea of the generalized harmonic numbers, because I will be using those in my next generalization bomb, Mr. Papa. But the generalized harmonic numbers are usually denoted like this, sometimes like this, but that makes me think of derivatives too much, so I personally prefer the double subscript, which is very simply this. So we're just going to do from k equals 1 to n of 1 over k to the m, right? And so this is the definition of the generalized harmonic numbers, right? We're simply raising the denominator to various powers. If m is negative, you're going to get sums of powers of integers, which is sort of answerable using Bernoulli numbers. But since m is positive, we have reciprocals. A few simple realizations that we can make. H sub m comma 1 is simply the regular harmonic numbers, right? Because we have the power of 1, and so it's just the sum over the reciprocals. H sub n comma 0, where m is 0, so all of these are 1, just gives us the number n. If h is -1, we have our triangle numbers, right? Because we're adding all of the integers, right? m -1 means this is getting reciprocated, so we're just going to get the triangle numbers, which is n times n plus 1 over 2, my mistake. And then there's all the other ones. But more interestingly is if we allow for n to go to infinity in this way, h sub infinity comma m, which is equal to the limit as n goes to infinity of h n m. So instead of writing all this, if I ever mean to write this, I'm just going to write this. This is actually just zeta of m, right? Because if n goes to infinity, then this is the whole sum from k equals 1 to n, and then the power is the input for the zeta function, so when n goes to infinity, we just get zeta of m. And we're going to be utilizing this fact today, and I'm going to need these later on in later videos to really, really attack the papa with my generalizations, especially since he got to the video that I wanted to make before I did. But I will not hold a grudge, because I will destroy you. Okay, so let's utilize those few things. So first we need to start off with, given what I just mentioned about the Maclaurin series for natural logarithm of 1 plus whatever, we're going to start off with the natural logarithm of 1 plus 1 over, let's do, I don't know, t, right? And this, of course, can be written as the natural logarithm, well, 1 plus 1 over t, we'll start there. Because of what I just mentioned before, this is equal to the sum from k equals 1 to infinity of negative 1 to the k plus 1 over k times t to the k, right? This is the Maclaurin series for that, in a sense. Or I guess in this, is it the Taylor? No, it's not the Maclaurin series. It is the Maclaurin, because it's not at 0. Yeah, all right. Whatever. It's the series representation. These things, I know they have a radius of convergence, whatever, I don't give a shit. It doesn't really matter. T is less than, 1 over t is less than 1, because I say so. And so we're going to simply write this as t plus 1 over t, right? Because t over t is 1 plus 1 over t, so it's the same thing. And we're actually going to double sum this bad boy right here. So we're going to write it as the sum from t equals 1 to n, and we're going to do that on this side as well, t equals 1 to n. Because if you recall from my video about the sum that equals 1 minus gamma, this is exactly equal to the natural logarithm of n plus 1. So this is log of n plus 1. If that's not clear to you, or why that's the case, write out the terms and multiply them out, add them all together, and then multiply the terms inside, or just watch the video that I did previous to this. And what I'm going to do is I'm simply going to exchange these sums because they don't depend on each other, and I get that k equals 1, the sum from k equals 1 to infinity of the sum from t equals 1 to n. I'm also going to factor out the things that don't depend on t, which is the negative 1 to the k plus 1 over k. So I get this sum out here, negative 1 to the k plus 1 over k, and the 1 over t to the k stays. But notice what I said before, this is actually just the generalized harmonic numbers, right? The sum from t equals 1 to n of 1 over t to the k. This is just h sub n comma k, right? And you can see why this is going to become the zeta function when n goes to infinity, right? So this is equal to the sum from k equals 1 to infinity of negative 1 to the k plus 1 divided by k times the generalized harmonic number h sub n comma k, right? That's from what I said before, right? And now what we need to do is simply isolate the first term of this to start. So I'm going to pull that out, and that means just plugging in k equals 1, right? So we end up with the natural logarithm of n plus 1, right? Equals, and then the first term, plugging in 1 here, gives us 2. So negative 1 to the second power is 1, over 1 is 1, so we end up with just h sub n comma k, comma 1. So h sub n comma 1, and then plus the rest of that series, which is the sum from k equals 2 now, 2 to infinity of negative 1 to the k plus 1 over k, h sub n comma k. Now, what is this? What did we say at the beginning? The generalized harmonic number of h sub n comma 1 is exactly the same as the nth harmonic number. So we're going to subtract that term over, so minus that over, and set that equal to that. Right? All I did was subtract that over, but this is very familiar. So all we're going to do is just flip those around, which will multiply everything by negative 1, so we end up with h sub n minus the natural logarithm of n plus 1 is equal to now the sum from k equals 2 to infinity of -1, and since one of the -1 powers went away, it's going to start at k instead of k plus 1 over k times the h sub n comma k, which is the generalized harmonic number. And now look at what we've got. Come on, I showed you this before. We're just going to let n go to infinity. Duh. And when n goes to infinity of this, what do we get? We get our Euler-Mascheroni. We get our Euler-Mascheroni constant, right? So says General Fibonacci. And if we're letting n go to infinity here, what did we say? We just get the zeta function, right? This is this thing right here, right? This right here. If n goes to infinity, then we're just summing over all t raised to the same power in the denominator, which is the definition of the zeta function. I mean, come on, guys, this is so f***ing awesome. So we get the sum from k equals 2 to infinity of -1 to the k times k of the Riemann zeta function evaluated at k. Absolutely beautiful. Just beautiful. Absolutely beautiful. Now remember, we could, again, generalize this because, not generalize it, but since the principal value of the Riemann zeta function at 1 is the Euler-Mascheroni constant, we can subtract it over and have it part of the sum and start the sum at 1, and then it would be equal to 0, but that's not as pretty, and it's not really equal to gamma at that point, it's just the principal value, but this is the real gem here. So I hope that was easy to follow. It's not a very complicated argument relative to what we already know, and it's beautiful. It's absolutely stunning. I don't really have much more to say about that. I mean, look at that. So if you plug this into like a whatever thingamajig and start summing, you'll get gamma. It's beautiful. So I wanted to go over one more series today. It might be in the next video, but you know, I'm going to do it right now. And that would be Vaca's formulation of the Euler-Mascheroni constant. And so I have to like parse this proof that he did and like come up with the argument to express it to all of you, because it's a very, very lovely, lovely argument. Quick little thing, this channel has an Instagram, so it is at what the hectagon, of course, and it has a Twitter, and it is of course naturally, also at what the hectagon, and my email is the incorrectly spelled what the hectagon, why spell check before you make the email right, that you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.